Hello, everyone. It's Professor Vallejo. Hope you're having a great day. Uh, Today, I'm going to go over measurement with you. And so let's get started. Want to remind you to go ahead and take your Cornell notes and turn those in after we're done here. And also, if you'll fill out the lecture participation form, that would be great. Okay. So we're going to share the screen with you. These notes are also in Canvas. So I encourage you to take a look at these notes after our talk. If you'd like to look at just the PowerPoint without the audio, that'd be great. So let's go ahead and get started. Measurement. Measurement's important in science because that's how we convey accurate quantitative data. You remember from the last talk when I was talking about quantitative and qualitative, when you have quantitative information, that is numbers. You know, my example was, I'm pretty tall, or hey, I'm 171 centimeters, and that is tall. So that is quantitative data. Now, if I use the metric system, I can effectively communicate with scientists around the world. And that's because everyone just about uses the metric system, which, by the way, has a new name, and I'll go over that in a little bit. As we measure, there are many things that we measure, but the four important ones I'm going to cover in this talk are length, volume, mass, and temperature. So let's take a look at those. So here's length. And I defined it this way because this is how it is on the quiz that you'll be taking later, the measurement of a line extending from one point to another. So point to point, that's what we're talking about when we're talking about length. When we take a look at liquids, when we want to know how much liquid we have, that's called volume. Volume is the space that liquid occupies, but solid objects, gases can have a volume as well. Volume is defined as then the space that something occupies. This is called an Erlenmeyer flask, and the Erlenmeyer flask here has some substances in it. These are little gummy bears. Caution, don't put food in scientific glassware. That's a no-no. That comes from my Don't Do This lecture from laboratory safety. A third thing that we measure is mass. Mass is the quantity of matter present in an object, which is different from weight. The amount of stuff inside you is not going to change if you get in a plane. But as you go up in a plane, let's say it's a really good plane, and maybe it's a space shuttle, your weight is going to decrease as you gain in altitude. So your weight is actually determined by the distance, it has to do with the distance between two objects. And so the greater the distance is, the less the weight is going to be. So that's not true for mass. Mass is the amount of stuff that's in something. So quantity of matter present in an object. And then there's temperature. Temperature, you probably have a good understanding of temperature, but just so you can be successful on the quiz, then it's known as the measurement of the warmth, or coldness, or the degree of hot or cold. Now, when we take a look at units of measure, back in the day, they would use their body parts for different measurements. So there's a yard, there's a fathom, there's a cubit. But in the United States, the one we probably use the most is the foot there. So what body part could be used for length? All of these, but really the foot is probably the most common one there. Most common to most of us, but to some people, when you're talking to people who have horses, any of you have a horse? If you're talking to people who have horses, you might talk about a hand, and you might say, hey, how tall is my horse? Hey, my horse is 16 hands tall. And so that's a common thing that is said in equestrian circles. And so as long as everyone knows about how big a hand is, because some people have smaller hands and some people have larger hands, then you get a good idea of a measurement. So you have to know about how much it is. Here's some measurements right here. Here's a list of things. I don't recognize all of them, but there's some I do recognize. And so any of these units could have been used to describe the same distance between Coalinga and San Jose. Now I know how long it takes to get to San Jose. Well, I want to go to a Sharks game. It's going to take me about 2.5 hours to get from Coalinga to San Jose. Well, that's about 150 miles. And that makes sense to me. Well, what if someone said to me, hey, you want to go to a hockey game? It's only 48,000 rods away. What does that mean? I don't know. Oh, San Jose, that is 452,000 cubits away. I don't have a good working understanding of that. That's because we live in the United States, and when one unit is officially adopted, it becomes known as the standard unit. For large measurements, for large distances, miles is the standard unit in the United States. But in most parts of the world, in other countries, they use the international system of measurement. I wrote Système International, and that's my French accent, because it was formulated in France. And so it's a new name for the metric system. And just about all of the world uses SI. Is that true? See, it is. Even the British don't use the system that we currently use in the United States, and the British would rather us call it the American standard. But here is what you might know. You might know there's 12 inches in a foot. Did you know there's 3 feet in a yard? Do you know what the next unit is after yards? And if you don't, that's okay. Most people will say a mile. But I'll tell you, when I get out of here, I gotta walk to my car. It's actually about 20 yards. No, not a yard, 20 rods away. A rod? What is that? Well, a rod is 5.5 yards. That's actually the next unit of distance. But no one uses that. So let's go back and take a look at yards. How many yards are there in a mile, do you know? I know that there's 1760 yards in a mile. That's my third grade teacher, Mrs. Sipping in Salinas, California, made us memorize that. She also had us memorize the number of feet in a mile, 5,280 feet in a mile. And that's about the elevation of Denver, Colorado. So that's why Denver is known as the Mile High City. Now, in this English system, look, you have to know these silly numbers, 12, 3, 5.5, 1760, 5,280. That's confusing. In SI, here's what you need to know. You need to know 10. So I'm going to ask you, what's easy to remember, 10? Or is it 12, 3, 5.5, 6, 17, 60, 5,280? It's definitely 10. So we should all use a metric system. A metric system, it's for big numbers, it's for small numbers, but they're all factors of 10. Now, if it was a really small number or it was a really big number, instead of putting a bunch of zeros on it, like Donatello and Michelangelo did in that remake of Teenage Mutant Ninja Turtles, one turtle asks the other, hey, Donnie, what's the chance we're going to get out of this alive? And he said, 0.000000003. Wouldn't really say that. He would use metric prefixes or something, or scientific notation to illustrate the point. So prefixes help us to avoid writing large or small numbers. And here's one you probably know. There's 10 millimeters in a centimeter. I'm at my desk right now, so I'm going to pull out a ruler. But each of these little marks here is right there. Each of these little marks is a millimeter. You can't see that, can you? A millimeter but they're 10 millimeters, and a centimeter is about this big. Okay, they're 2.54 centimeters in an inch. Here's some other ones you may not know. 10 centimeters in a decimeter, 10 decimeters in a meter. A decimeter is about this big. And a meter is a little bit more than a yard. Here's the second one you might know, kilo. Kilo is a kilometer. So some of you like to run, I know. And so when you do a 5K or 10K, you have an idea of that distance. 10K, 10 kilometer run is 6.2 miles. That means a 5K is 3.1 miles, so it's half. And there's 1,000 meters in a kilometer. So these prefixes tell you how many or what part of the base you are using. But if you didn't grow up with metrics, how do you remember all these prefixes? Well, I want to give you this mnemonic, which, by the way, is your key phrase for this lecture. King Henry died by drinking chocolate milk. That'll help you to remember the order of the prefixes. King Henry died by drinking chocolate milk, right? So that's how we remember those. Because SI is based on 10, well, all you have to do is move the decimal point over. But which way do you move it? Well, if you're going from smaller to larger units, you move the decimal point to the left. Mathematically, that's dividing. And when you're going from a larger unit to a smaller unit, you move the decimal to the right. The trick is, how many spaces do you move it over? Well, let's try some from today's, or actually this week's lab. This week's lab, we have some conversions to do. Here's number one. 2 meters is how many millimeters? Well, this is larger to smaller, so what we're going to do is we're going to multiply, and we're going to multiply by 1,000, because in our phrase, it's King Henry died by drinking chocolate milk for millimeters. So there's going to be, you're going to multiply by 1 with 3 zeros, or 10 to the third power. So that's how you do that. Now, if that's confusing to you, because a lot of people, or a lot of times, a student or 2 or maybe 5 will come up after this talk and say, I didn't know there was going to be so much math in biology. Am I going to be okay? You're going to be okay, because I'm going to give you this metric conversion chart. This metric conversion chart is going to help us do this, and we're just going to move the decimal point over one way or the other. So 2 meters to how many millimeters? Let's see. I gave you a better copy of this chart in Canvas, so download that and print that out, and then you can use that. The first step is to place the decimal in the right place. There's the decimal, and there's the number. So I got 2 meters, and I want to convert the 2 meters to millimeters. So I'm going to take this decimal, I'm going to move it over to the millibox like that. So I've got this decimal right here is no longer counting for anything. And I do have some empty spaces right there. So what I want to do is fill those in with zeros. So my answer is 2,000. And if we go back, you see, yes, the answer was 2,000. And again, I place the decimal, place the number, move the decimal, and fill in with zeros. So that's how you do that. Place the decimal, fill in the numbers, move the decimal, fill in the blanks with zeros. Pretty standard, but let's do another one. Let's say we're going from millimeters to kilometers, and we got 2,000 millimeters going to how many kilometers? Well, we're going from smaller unit, milli, to a larger unit, kilo. So mathematically, we're going to divide, but what we're going to do really is we're going to move this decimal over to the left. You can see the answer already if you divide 0.002. I got to divide by million. How do I know it's a million? Because it's from milli to kilo. Or looking at it the other way in our phrase, it's from kilo to milli. It's from king to milk. So King Henry died by drinking chocolate milk. That's 6 zeros. So I got 6 zeros right there. I'm going to divide by 6. I get 0.002. Now, if that's confusing to you, then look, use the chart. So let's take a look at the chart again. We got 2,000. I'm going to put the decimal in and put the numbers in. Then what I got to do is move that decimal point over to where I want it. I want to move this decimal point over from here to the kilo. So it looks like that. Do I have any blanks? Do I have any spaces? And I do. And it goes 0.00. So it goes 0.002 is our answer. And that's what it is right here. So mathematically, you can do it. Or, you know, if you grew up using this, you probably know the prefixes in your head anyway. I certainly could move it over and figure it out without paper and pencil. But if you can't do that, then use them at the conversion chart. Even on the quiz this time, you can use your chart. Right, 0.002. There's some other topics in measurement I'd like to cover today. First, the idea of an uncertain number. You look at this ant. I'm trying to measure the length of this ant, and it's more than a centimeter, but less than 2. That's a pretty big ant. But let's say they got 1.5. It's more than 1.5, but it's less than 1.6. So I'm going to guess that last number and say it's 1.52. That 2 is called the uncertain number because I couldn't measure it because there wasn't a line. It was uncertain. So that's how I got 1.52. So that's called the uncertain number. Now, another topic in measurement is significant figures. If you ever had a chemistry class, you might be familiar with significant figures. Says here the numbers recorded in a measurement, including the uncertain number. The number that we just saw, 1.52, has 3 significant figures. These numbers all mean something. So these are the numbers recorded in that measurement. There's 3 we say in chemistry. We say 3 sig fig. Now, there are non-zero integers, 1, 2, 3, 4, 5, 6, 7, 8, 9. All of those are significant numbers. So in this example, it says how many sig fig? Well, there are 4 sig fig, 5, 6, 8, and 9. Zeros are a little weird, so being different, there are rules for the zeros. If your zeros are on the left side, they are not significant. So none of these zeros are significant. And so the answer to our question, how many sig fig, is 3. Only the 4, 5, 6 are significant. Over here, hopefully you see that there are 2 sig fig. Now over here, there's only 1 sig fig. Because these numbers to the left of these non-zero integers are all not significant. Now, captive zeros are always significant. Like in the zip code, those 2 zeros are significant. So there's 5 significant figures. If you've ever been to LA, you have probably had to drive on the 405. That's 3 significant figures. But if you look at this 0.0405, that 0 is not significant. It's to the left of these significant numbers. So there are only 3 significant figures, not 4. Sometimes to make it more clear, what we do is we underline this 0. Even by rules, by the convention, we can figure out that this is significant. But when we underline it, we make it more clear that that is a significant number. And then numbers on the other side, they're called trailing zeros. And these trailing zeros are significant if a decimal point is included. So here there are 4 zeros, or 4 significant figures. Here, did you get the answer yet? It's 2 sig fig. That 0 is significant because there is a decimal right there. Is there a decimal there? then that zero is not significant. So this also has 2 sig fig. This one right here does have a decimal, and we underlined it for you, so that makes it 3 sig fig. So trailing zeros are significant if there is a decimal. Now exact numbers constitute significant figures also. It says here the procedure was attempted 7 times. Well, you're not going to have, as an example, they say, the average American family has 2.7 kids. Not like you count your kids and say 1, 2, you're 0.7, Junior. And so that each one is either a person or not a person. There's not a 0.7 person. So significant figures, when you count, all those numbers are significant. Or if you have a definition, here we have 3 significant figures, 2.54. So if you have a definition with many, many more known numbers in the definition, then you would count all those numbers that has significant numbers, had significant figures. Like some people know the value of pi to an amazing number of digits. There's actually a phrase you can Google if you're interested in that. I only know that pi is 3.1415. Well, my friend Victor can go to like 11, 12, 13 digits. There's a sentence, just like our phrase, King Henry died by drinking chocolate milk, called a mnemonic that could help you memorize things like that. These rules you probably know. These are the rounding off rules. If it's less than 5, you round down. If it's more than 5, you round up. If it's equal to 5, then you would, if it's equal to 5, then what you do is round up. That's by convention. So yeah, 1.52, round off to 2 significant figures, that's 1.5. And so right here you have 3 sig fig. So we're rounding off to 2, so that's 1.5. Here you round off to 2 sig fig. You want to get rid of that 6, but are we going to make this a 5 or 6? You round that to a 6 because this is more than 5. That's how we get 0.0036 because we're going to change that to 6 because we're going to round it up. Let's have you try this one. 1.55, round off to 2 sig fig. What's that? If you got 1.6, that is the correct answer. Now, round off after you do all your calculations. Don't round off and then put it in the calculator. Put all those numbers in because that may affect your answer at the very, very end. So round off at the end. Here's some things to help you to finish completely the lab for this week. Water, by definition, has a mass of 1 gram. If you have 1 milliliter of water, so I wrote it this way, 1 milliliter equals 1 gram. This is a way to convert from mass to volume. So if you have 1 milliliter of water, then you already know that that weighs, it has a mass of 1 gram. If you have 4.2 milliliters of water, then you know that you have 4.2 grams of water. So they're 1 to 1, they're exactly the same. And then also, another thing you need to know to complete the exercise this week is the value of density as we measure. Density is the ratio of mass divided by volume. There's mass and volume, which gives us density. Density is a built-in value. It's an intrinsic property. It's independent of quantity. So if you have a big bar of gold, it has a density of 19.3. But if you have a little piece of gold, it also has a density of 19.3. So if you have a piece of rock and you're trying to figure out if it's pure gold, well, then you can figure out the density, and then that would tell you if it's 19.3, you would have an actual piece of real gold. This characteristic doesn't change no matter the quantity, and it's specific for different chemicals. So a characteristic of a given material. This density is measured in different ways, or the units are stated in different ways. We have grams per cubic centimeter, which is also written this way. And this is centimeter and this is cubed. So gram per cubic centimeter. But by definition, a cubic centimeter of water is the same as 1 milliliter. So we could say gram divided by milliliter as well if we were studying density. Okay, so measurement is important in science. So hopefully I've given you some insight into different things that we look at in science when we are considering measurement. Good luck on your quiz this week, and we'll see you next time.